What? Hang on. This. Last time we basically finished the parametric equations section 10. We basically did 10.6 and 10.7 together all at once. 10.6 is what parametric equations are and how to parameterize a curve, all that kind of stuff. 10.7 is about graphing, and it doesn't make sense to me to do them like separately. They're so tied together. I'm guessing no one's had a chance to try that out yet. I did have some questions in my office hours from those. What about sections before that? What about 10.4, 10.5? Is that going okay? All right. Try to drag questions out of you. All right, so if nobody has questions, we're gonna plow ahead. Am I okay? I don't know. I'm a little concerned. Whenever I don't have questions from people, I get concerned. So I worry about you guys. I do. I don't think you think I do, but I do. So I'm worried. I'm worried about the people that aren't showing up. I'm worried about the people that don't ask questions. I'm worried in general. So it gets to me. But thanks for asking. I think I'll be okay, maybe. Oh, okay. All right. Understood. So if you're behind on homework, I understand that. I do. The thing is right now, so the last quiz we had was on 10.1 through 10.4, if I remember correctly. If you're not done with that homework yet, 10.1 through 10.4, kind of let it go a little bit. Yeah, because the next quiz is coming up faster than you wish it would. And it's going to be on the end of chapter 10. And don't forget, I didn't put section, I think it was section 10.4 on the last quiz. That was graphing polar equations. So that's going to be on this next quiz. Yeah, so basically 10.4, 10.5, 10.6, you want to get in that homework right now, especially if you haven't started any of it. If you're doing 10.1 homework right now, get it done eventually, but maybe not right now. You want to be working on the homework that's on the next quiz. So you got questions for me so that you don't have to ask me if I'm okay, as I sit here and almost cry that nobody's asking questions. Okay, so do that for me. Because I keep telling you, this homework is weird. You're not expected to understand it fully when you first try to do it. That might be different than your experience in earlier math courses, maybe. I don't know. But that is the way things are. It's supposed to push you a bit, and you can't always make the connection by yourself. And that's why I try to let you ask questions. Plan to work on 10.5. Okay. Is the next quiz still May 17th? As far as I know, it is. I haven't considered moving it.
I have a question.
Yeah.
So the question I asked you earlier, chapter 10.7, 36.
All right, let's see. 36. Yeah.
Do you use did you use the t values like a little bit smaller than like pi over 12 or something?
Yeah, you might need to.
Okay, because that point wasn't enough.
I think, yeah, and that's when you're going to just go ahead and use the calculator to do it. That's fine.
So how do you pick all the points for t?
Well, you do just like you did. And this is why the example I did the other day, I left room between. Remember, we had a problem and I set up the TXY table, and I had Jeff. I put 0 and then I put 1 and then I put 2. I left room between so that I could put 1/2 in if I needed to.
Oh,
This problem, you're going to have like, so you can kind of do like you started to do negative pi, negative 5 pi over 6, and slowly approach 0.
Yeah.
But leave some room in the middle in case you need some more resolution. Maybe you do need the negative, what the hell would it be? 11 pi over 12, right? More resolution, yeah.
so I also wonder, can you go for number 51 too?
All right.
So
So on the graphing calculator or on Desmos, I'm not sure. I haven't tried Desmos for these kind of problems. I don't know if it can do it. On the domain 0 to pi, blah, blah, blah. All right. So what's the trouble?
So since it's from 0 to 2 pi, and also like you kind of know how the graph is gonna look like.
You do? That's neat.
No, when you use a resolution and you get the values, right? And then you kind of know like when. So you cross the 2 over pi over 2, it's kind of going down.
I mean, once the inputs reach pi over 2, and of
Yeah.
course their periods are going to be different because you got different values for A and B.
Yeah.
That's going to affect the period. So it's not as easy to think ahead of time what this is necessarily going to look like.
So
And remember, X and Y together are changing like sine, which means the points X is going like sine and Y is going like sine. So when you plot the points X, Y, it's really, really difficult to know ahead of time what it's necessarily going to look like. I know it's going to be curvy because both X and Y are related to sine, but
because I thought it's like if you do like a the denominator equal to 12, it's gonna be a lot of chart.
I'm not sure. Okay. All right. So
You have to make like 24 of them.
you're sounds like you're doing way too much work because they want you to do this in the graphing calculator. You don't have to make a table. You
Oh,
just have to put in the graphing calculator, right? It said use a graphing utility, right? So let me show you real quick. Remember this little dude we got last time? Oh, all right. So if I put in here, let's put something here. Let's do cosine. Let's do cosine of 2t and cosine of 5t. Okay, so same problem. I'm just using cosines instead of sines. Is that cool?
yeah.
All right. So if I go to the window, I can control what t goes. So I want t to go from 0, get out of there, negative, to 2 pi. Pop. This, I think it defaults to 0.1 something. I always make it 0.0 something just so it's got better resolution. You don't have to consider what your step size is going to be. And I can't remember if they gave you X and Y. Let's see. Now I'm curious what this is going to look like. Oh, look at that. Isn't that cool? Wiggly. It's a wiggly dude. No, yes, no, yes. Now, one thing you could predict, I don't know if this is maybe what you're talking about. I know that it's X is going to be between -1 and 1, Y is going to be between -1 and 1 because they're trig functions. I just don't know exactly how they're going to fill in the space in between. So what if I make this 3t? That looks different, right? That looks like a pretzel. I love it. No, yes, maybe. So that's all they want you to do. Plug it in the calculator. Set it up like they ask you to. And you can just take a snapshot of it. Is that all right?
Oh, okay.
Yeah, nothing crazy or nothing too crazy. And look real quick. Look at this real quick. All right, let me, I don't know. I'm pretty sure I signed some out of this section, right? Have you tried any of these yet? They look like atomic models or something,
Oh, yeah.
right? Can you guys see these problems here? Look, there's the fish. There's the comet. All right. And the instructions are figure out what the hell A, B, C, and D are to make this happen. A and C, stay with me. I'm trying to help you out on parts of your homework. I'm pretty sure I signed. Rio, can you help me out? Do you know if I signed one of these problems? Like 54 or something?
Yeah, 57 to 60.
Oh, I didn't assign anything in here?
54.
54 I signed?
Yeah.
Okay. So look at this one. What do the X's go between?
-4 to 4.
Yeah, so for the X's, what should A be?
4.
All right, let me stop for a minute. Everybody understand? I really, listen, this is huge. This is not difficult. This is easy, but it's going to help you figure out these parametric equations. So in the X direction, it's bounded between -4 and 4, which means the trig function that X is dependent on better have an amplitude of 4. Now, somebody else tell me, what's the amplitude for Y going to be? What's the value of C going to be?
6.
6. Yeah, exactly. So you know what A and C are. Now the only thing you have to figure out is what B and D are. And can somebody please tell me B and D, what do they affect on the cosine function? What do they change? When I change B, when I change D, what changes? What corresponds to that? Who remembers?
Yeah.
The period. It's just like the K value. Remember the K value that changes the period? Not the stretch. That's the amplitude. All right, I'm with you. It's like a compression or yeah. When the x is right. All right. In this case, it would be the t axis, which is weird, but it's kind of related to how many of these fit, how many kind of cycles fit in here. But the nice thing is, you're using your graphing calculator. You can kind of change B and D until you get this sucker to show up. You can kind of do a trial and error. And they want you to realize when you find the right values, the A and C are pretty straightforward. They're amplitude. They're very straightforward. The B and D, not quite as straightforward, right? But once you figure out what they are, they want you to go, oh, it's the period. I could see it's how many of those fit in there. All right, so this is just going to be some playing with your calculator to do this. Okay. No, yes, no, sucks. Stop helping me with my homework, Jeff. Okay, no worries. Any other questions from homework stuff? All right. There are some problems that get weird. Again, they do. I've assigned problems that push you. I do. I often do that. So don't sit there and feel like I'm the only one that doesn't understand, so I'm not going to ask because I don't want to look silly. No, you will be other people's heroes for asking, if just for one day. Okay. Anything else, guys, before I get into the next idea, which is huge? The nice thing is the next idea is not new, but it really packages everything we've done in a different kind of way. So it's going to feel very familiar, is the hope. Okay. All right, so let's do this. All right. I don't see any more questions coming in. Let me turn off my background, make sure my house isn't too messy. Bam. I got this too. I can make it blurry, but no, that's not good. Now, a lot of what we do with these things, they start to feel repetitive, but there are distinct differences. Polar equations and polar coordinates, the ideas can be used in parametric stuff, but parametric is more general and it allows you more control over each individual part of a point, X and Y. All right, I like it, maybe. What we're about to get into are things called vectors. When I say vector, what do you guys think? Does that cause you to think anything when I say vector? Does it make you think about anything? Anybody?
Direction.
Okay, direction. I like it. There we go. I was waiting for it. I was waiting for it. The bad guy. Sorry, go ahead. Somebody else was saying something. I'm sorry. I talked over you. Anything else? Nothing else about vectors comes to mind?
Speed and
yeah,
or measurement.
I like it. So one place we use vectors is in wind to define wind. Committing crimes with both precision and magnitude. Yes, I like it. Wind. So wind has a direction and it has a magnitude. Yes, magnitude is not just a character from the show Community. Magnitude is, I don't know if anybody's ever seen that show. Magnitude is just another name for the length of the vector. So if I had wind that had a large magnitude, that means it's got a high speed. It's a high wind velocity. Maybe. So a vector has direction and magnitude, right? So you can talk about a velocity vector. You could talk about a wind vector. You could talk about a force vector, right? Is everybody with me so far? So for example, if anything on the Earth has a down vector that has the direction is toward the center of the Earth, and the magnitude is equivalent to its mass times acceleration of gravity. So that's a force vector. If I push on a block, the force that I'm exerting has a vector associated with how strong I push and the direction I push in. I like it. All right. Okay. So. Where do I want to go with this? So let's talk about the technical aspects, and we're gonna at the same time we're gonna talk about the graphical aspects of vectors. They really go hand in hand. See, how's that? Is that all right? What do I have up here? I have, I got statistics. All right. Let me see, where am I? Oh, let me do this. I keep forgetting this. For some reason, I've suddenly stopped doing this. Okay, there. I gotta make it all about me because I don't want you guys to have to worry about showing up on the YouTubes. All right. So we got vectors. So we're gonna build our way up to, but vectors are basically things that have direction and magnitude. So for example, a really good everyday experience, when I say velocity, is that the same thing as speed? What do you guys think? Velocity, speed. Yeah, they're not the same thing. Velocity is a little more complicated. Speed is the length of the velocity vector. So velocity is speed plus direction. Speed is just speed, right? So if I said his speed was 50 miles an hour, I have no idea which way it was going. If I give you the velocity vector, I know which way they were going and how fast they were going. Okay. So let's talk about a little bit about the graphical idea behind vectors. Graphically, I've got an initial point. I've got terminal point. And I don't know if you guys remember, this is not going to really come up, but do you guys remember what this is in geometry? If it kind of went forever, this would be like a ray. So this is a weird thing. It doesn't really fit into geometry because it doesn't go forever, but it does have an arrow. It does have a direction. So in geometry, a ray it has an initial point and it goes forever in a certain direction. So it's not a full line. It doesn't go forever in both directions. I don't know. Does anybody remember that? Rays? That's why we call them sun rays, because they originate at the sun and they theoretically go forever from there. Okay. So that's not what we have going on here, because this doesn't go forever. It stops at that point. So if I wanted to give this thing names, how do I name this thing? I could either say, let's say that this is point P and this is point Q. Then this guy's name would be PQ. It's crazy. But we put PQ with a little, I always do it like that. You could do it like this too. I just do it like that for speed's sake. Okay. You guys all with me out there so far? Nothing amazing. So if I actually had point P and point Q, but it went this way, what would you call this vector?
QP.
QP with the little line over it. I love it. So it does matter the order. Yes. Initial point to terminal point. I like it. I could also give it a name. I could just call it, let me get rid of him. I could actually just call this thing, I could just give this the name U vector. I can call it the U vector. U, V, W, those are like X, Y, Z. U, V, W are like the variable, the letters that we assign for vectors. Same way we assign X, Y, and Z for normal variables in algebra. You guys with me? Okay, nothing amazing yet. So another name could be U with a little line over it, or V, or W, blah, blah, blah. In the book, when you see something typed, you could actually just have this in bold. Since I can't really do bold easily up on the board, I'm just going to use a little vector symbol. Obviously, I can't really do bold too well. Okay, I like it. I like it. Nothing amazing yet. Now, there's one more way to identify a vector. Let me see. If I pick this vector up and move it here, let me see. Say I've got my coordinate plane. So this vector is sitting on this coordinate plane. What if I pick this vector up and put it here? Will it be a different vector? If I pick that vector up and move it here, would it be different? Why am I so shaky? Is everything shaking for you guys? I don't know. It's kind of driving me crazy. No? Okay, good. My screen is like, all right. So it's just on my side. Man, that's crazy. Sorry, it's going to drive me a little crazy. My screen's like, what? All right. No. Everybody cool with that? Everybody understand? If I pick that vector up, it's the same damn vector. All right. So let's say it starts at 0, 0, and it goes to A, B. If it is starting at 0, 0, and it points to the point A, B, then I can call it A, B, like this. Now I can almost hear you guys silently screaming in your brains, like, why are there so many different freaking ways to identify these stupid little things? Well, it's just the way it is. There's different reasons. This is the least used, in my opinion. These two are the most often used. This is good for theoretical things, like it's not really a vector that has a standard position. right? It's just the vector u and the vector v, and I don't know what the points are. This one obviously is used when they actually have standard, and this is what this is called. This is called the standard position. When you put it starting at the origin. So let's do a concrete example. Yes, let's do a concrete example. Okay, I'm gonna erase all this. You guys ready? Because I got a tiny whiteboard. Poor little dude. All right, here we go. Let's see. Yeah, sure. I'll go to you. All right, so let's say that I've got P is -2, 1, and Q is -3, -3. So I can identify this as PQ, but I want it in a better way. So let's graph this real quick. So -2, 1, -2, 1, and -3, -3, negative. No, Jeff. I'm sorry. Change this to +3. Yeah, I'm sorry. I don't know why. It doesn't really matter, but it just goes better with how I've drawn this. 3, -3. So make that 3, -3. All right. So here's the vector we're talking about. So right now I've got to call it PQ. But I want to be able to call it what the name I can give it if it was in standard position. Now, this is nothing amazing. This is nothing crazy. This is nothing too big. Again, if I could grab it and move it, couldn't I just move it over so that this actually starts there at the origin, right? How much would I have to move it? How much would I have to move it over and down so that this starts at the origin? I think you said 2. Yeah. So I have to move it 2 over and 1 down. So of course, if I pick this up and move it 2 over, 1 down, this also goes 2 over and 1 down. So where does this end up? What's this?
5 minus 4.
Yeah, this is 5 minus 4. So now watch how I can do this algebraically. This should not come as a big surprise. How can I do this algebraically? I take the terminal minus the original. It's a little bit like slope. No, Jeff. -3. You could do it, Jeff. Get it in the right place. 3 minus -2. And then -3 minus 1. That effectively does what we just did visually. I don't want to have to always graph these things just to get them in standard form. So now another name for this guy is 5, -4, which matches up exactly with what we just got. So in general, if you have 2 points between which lives a vector, you take the terminal minus the initial, to figure out what its name is in standard form. Standard position. Okay, nothing too crazy yet, right? We're just plopping a line segment down with the direction and we're moving it around. Ooh, okay. So now we can start to talk about, all right, how do we find the 2 things you told me a vector is all about, Jeff? Now we got some names for these things. How do I find the direction and the position? So let me leave this up here. Direction. I'm sorry, direction and magnitude. Let's talk about magnitude first. How would you figure out how long this thing is? Right, it's sort of like R, right? from polar? How would I figure out how long that thing is?
Use the Pythagorean theorem.
Yeah. Pythagorean theorem, right? Which is the same thing we do for figuring out r. Isn't r squared equal to x squared plus y squared? So here's the symbol for the magnitude of a vector. So let's call this thing v. Cool. Let's call this thing v. This is the v vector. So the magnitude, here's what's kind of funny. The magnitude is this. Now, what does that actually look like? What do those symbols mean for us normally? Man, I need a haircut bad. What do those symbols mean for us normally? I mean, if I put this down, what would it be?
5.
5. Now, we realize what this means now. If I had a vector, what would its length be? It would be 5. So that's kind of like the length of a vector with just one dimension. Oh, so absolute value symbols, when you go to higher and higher dimensions, they do mean length. They mean distance. They still mean what does absolute value actually mean? Why does it always come out positive? Because it means the distance from 0, correct? So if I said how far from 0 is this point, you would figure out the length of this. So this still means the distance from 0. It still means the same thing. So that would be the square root of, why did I go so far? Oh yeah, of negative 4 squared plus 5 squared. Square root of 41. Is everybody with me on that? That should feel very familiar. Maybe. Yes. Are you guys okay out there? This all should feel very familiar. We've got some new terminology. We've got some old stuff that we're using in a new kind of way. But this should all feel vaguely familiar. That's what I'm hoping. Right? Because vectors just sort of like build on stuff we've done before. Okay, so what about the direction? Well, this also borrows from polar. The direction is going to be this angle. How am I going to figure out what that angle is? Now I can think about it like this. I should have done this way in the first place. But oh well. You could do it. How did we figure out theta when it was rectangular to polar? What did we use? You can do it. You can do it. How do I figure out theta? XY to R theta. How do I figure out theta?
Inverse cosine.
Not inverse cosine.
Tangent.
Yeah. So theta will be the inverse tangent of y over x. In this case, it'll be, well, I haven't written that yet, have I? Yeah, it's okay. Y over x. So in this case, this specifically is going to be the inverse tangent of -4 over 5. And then whatever the hell that is. I have no idea. Okay. Okay, all right. I think it's going to be something like 0.7 radians.
Yeah, 0.7.
It is? Wow. Sorry, that's just neat. All right. I didn't do that ahead of time. But anyway. All right. So that's roughly 0.7 rads. Okay.
Negative.
Right. Sorry, go ahead.
It's negative.
Negative? Yeah. Okay, thank you. That makes sense. Negative because I draw. Yeah. Bam, bam, bam. Okay. All right. So that's all this stuff that feels very familiar. Let's do another example real quick. I'm going to erase all this stuff. Here we go. Well, not all. I'll leave that for now. So if I have vector u starts at you do it, Jeff. It doesn't matter, does it? No, it doesn't. -4, 1, and it goes to 3, 5. All right, so 1, write it in a B form. 2, find magnitude and direction. Uh-oh. Am I frozen? No, I'm not frozen. Jordan, are you still there? Let me see. Okay, as long as you hear me. Am I moving around? Everybody I can see is moving. That's good. Let me catch up to you guys here. This is nothing, this is not taxing. This is not difficult math. This is old news math. So how do I write this in this form? I would just do 3 minus -4, 5 minus 1. Is that cool? That's almost too easy to believe. And again, if you take a minute and you graph this, -4, 1, and 3, 5. It's this vector here. So if I move it down there, then it should be there. So 7, 4 makes sense. I don't know if anybody followed me there. So if you graph the 2 points and you consider moving that vector here, 7, 4 makes sense. Uh-oh. Is my Wi-Fi going crazy? Looks okay. All right. Sort of sketchy. All right. I am sort of sketchy. So how do I find, now that I've got it written in standard position form, it's going to be easy to find the magnitude. Magnitude, did I call this anything? Yeah, I did, vector u. It's just the square root of a squared plus b squared. 49 plus 16, that'll be 65. And then the angle. And again, you're going to have to consider kind of which quadrant you're pointing to, right? Because when you do inverse tangent, it might be a reference angle. You could do it, Jeff, 4/7, and then whatever that is. I'm not going to try to work the magic again. Anybody manage to get that inverse tangent of 4/7? Is there anything up here that doesn't make sense to somebody out there? You gotta let me know.
5.19 radians.
0.519? Yeah, that's what I got. Or almost 30 degrees, which is kind of neat. All right, so I got direction and I've got a magnitude. This is roughly 8 point something or other. Okay, all right. So if I had a wind vector like this, it might mean 8 miles an hour going almost 30 degrees north of east. Does that make sense to you guys? Here's east. So this is north of east. 30 degrees north of east. Okay, maybe, I don't know. All right. Okay. Vectors, once we create these things called vectors, it opens a whole new way of doing mathematics on different things. And again, there are some things I can represent as vectors that I don't have to represent as vectors, and the math might be easier if I do or if I don't. But vectors themselves exist. That vector exists. It doesn't have to represent wind. It doesn't have to represent velocity of something, somebody's car moving. It just is a mathematical object, like the number 7, right? So vectors are math objects just like numbers are. Okay, we can just use them to define different things. All right, let me get rid of all this. This shouldn't be too evil, I don't think. Old stuff down here. Now comes so let me I really want you guys to understand this. This is just so cool. When you learned about numbers 1, 2, 3, 4, 5, 6, what did you do with them kind of next? You what is 1 plus 5? You started, how do they interact with each other? What are the operations that we can use between two elements from this set of things called numbers? Okay, why am I talking so weird? I don't know. All right, maybe. So now we've got mathematical objects called vectors. What would it mean to add them? What would it mean to multiply them? All right, let's find out. All right, so for example, let's say I've got the vector. What do you wish would happen with this? Let's say the vector 1, 3 plus the vector -1, 2. What in your wildest dream would it mean to add these together? What do you wish it means? Please let it mean this, Jeff. Come on, you guys can do it. What do you hope? How do you hope this would work?
Does it change the direction?
It's obviously going to have to change the direction. So one conceptual way to think about this is if somebody's pulling a block with this force vector. Are you guys with me? Does that, you can even think of this as a rope. So somebody's pulling it like this, and somebody else is pulling it straight. You guys all with me? When I add these two together, let's say this is 8. All right, I'm just going to use the force. It's called newtons, and that's like a unit of force. Okay, and let's say that this is 5 newtons. Do you think that they're pulling on it with a total of 13 newtons? Do you think that makes sense? No, exactly. How much of this guy is acting with this guy. Isn't it just this piece? Isn't it just that piece? Okay, I like it. Austin's got a guess, and I think Bowen has the same guess. And I will tell you that's true. Thank God, right? This actually is 0, 5. Now let's figure out why that makes sense. Why is that? So thank God, right? Thank God. Thank God. Or thank, whatever your favorite deity is. I don't know. I don't have one. That's all right for me. Blind spaghetti monster. That's mine. So let's see. Why would it be this? Thank God it is. But why is it that? So let's take a look. I kind of want to take a little side note here. Let's see how much time I got. Okay, I got plenty of time. Too bad for you. Haha. Look at the vector 1, 3. So let's draw the vector 1, 3. All right, so the vector 1, 3 is right here. Scheisse. Jeff. It doesn't have to be. Okay. All right. It's Jeff. Hold on, everybody. I don't know why I'm suddenly. Okay. There. All right. There's the vector 1, 3. All right. The vector 1, 3 is itself made of 2 vectors added. How much of this vector is in the x direction? You know the answer. Is that cool? 1. This vector is 1, 0. Is that cool? How much of this vector is in the y direction? Somebody else.
0, 3.
3. So that is the vector 0, 3. Like you said, I like it. Right? Are you guys with me? Are you guys all with me? So what's kind of funny about explaining how to add vectors is when you write a vector like 1, 3, it's already a composition of 2 vectors. It's already the result of an addition itself. So 1, 3 is 0, 3 plus. Why are you using so much color? It doesn't matter, Jeff. 1, 0. Isn't that kind of silly? So, I mean, on the surface, if you just look at it like that, of course, that's how you add vectors, because that's how any vector is created. It's got an x piece and a y piece. And of course, thankfully, we're not talking about 3 dimensions. I could have a 3-dimensional vector, but we're going to keep it flat. Okay. All right. So we're all flat earthers today. So a little bit more about this. What's really, 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 really cool is we give. All right. There's an idea of, I've got a lot of things to tell you, and I'm not sure what order to do it in. There's an idea of what's called a unit vector. All right. Where else have we used the word unit? A dog is an absolute unit. No, in this class, where else have we used the word unit? Maybe trigonometry? Does that ring a bell? Yeah, unit circle. There we go. I had to look at the chat. Why was it called the unit circle? Why is that a special circle? What is it about the unit circle that's special? You guys remember? What's the radius of the unit circle? 1. There you go. So if you see the word unit in mathematics, it almost always will mean 1. So the unit vector, any unit vector is a vector with a length of 1. Unit vector is a vector with a length of 1. So the unit vector in the x direction, we call that I hat. I hat is the vector 1, 0. That's the unit vector in the direction of x. Now think about it. Think about how math people work. What do you think we call the unit vector in the direction of y? That's I hat. I'll bet you anything this is going to be.
Imaginary.
Let's see, we got vectors are u, v. We got variables are x, y, z. So if that's I hat, I'll bet you anything in the y direction. There you go. We call it j hat. J hat is the vector 0, 1. And if I was talking about 3 dimensions, k hat would be in the direction of the z axis coming out of the board, coming right at you. All right. Enough of that. So I just wanted to introduce that now, since we're talking about breaking vectors into components. This is what we really did. We broke this vector into components. We got its y component and its x component. So this, do you guys see this? This is I. And what do you think this is? Is this j? Is that vector j? No. How many times bigger is this vector?
2.
So this is not j, it's 3 times bigger. This is 3 j hat. So another way to write this vector is, let me write this in alphabetical order. It's I hat. I don't know why you got to be all colors, plus 3j hat. That's another way to write 1, 3. Oh my gosh. Okay, is everybody with me? There's a lot to kind of take in, I know. So a lot of this stuff is just sort of, which convention do you want to follow? Some of it is, some of the stuff we have to do with vectors is easier if it's in this form, or it's easier if it's in this form. You know, so we got all these forms to write things in. Okay. All right, now let's take a step back. All right, so now we can talk more easily about, now vector addition just makes sense. We're adding up all the I stuff. There's 1 I minus I, so that's 0 I's. That makes sense. All right, I'm boring the hell out of some of this. So let me erase all this stuff. And we're going to talk about something else that we just did here, but I really want to make sure you guys paid attention. Oh, let me do the visual. All right. Jeff. So we just did, what were the 2 vectors again? Did I have them plotted and everything? Good job, Jeff. What was it? 1, 3 and -1, 2, right? Okay.
Yeah.
Thank you. All right, so 1, 3, that's 1 vector, and -1, 2 is the other vector. Do it, Jeff. Why did I make it so tiny? I don't know. And somehow the answer comes out to be 0, 5. Now watch. Let's see if I did my scale well enough here. I'm gonna have to. I did my scale horribly, but that's all right, Jeff. Everybody's used to it. Okay. So watch this. It's kind of cool. All right, stay with me. This is the visual way to do vector addition. My scale is so bad. All right, I'm just gonna fudge it so it comes out right. If I draw this vector on top of this vector, so I basically take him and draw him here. Do you see how that's the same vector? Can you just pretend like it is? You guys with me? So if I pick that vector up and put it here. So now do you see why this makes sense that this is vector addition? I went this vector and then I added to that vector this vector. So it's sort of like
the two vectors are telling me which direction and how far to go. So if I go this direction and then this direction this far, I end up at the result of it adding them, which is 0, 5. Now I could have taken this vector and put it here, and it would have been the same thing, right? I don't know if you guys are with me or not. So if I take one of the two vectors I'm adding and put it tail to head, that is visually how to add two vectors. And do you guys see 1, 2, 3, 4, 5, how it matches up with the answer we got? Of course, I fudged it a little bit, but if my scale was perfect, then it would match up perfectly, right? My scale is never perfect, so that's okay. All right, maybe. So you have, oh, let me show you. Yeah. Let me show you this. This is kind of cool. Oh, let me make this official here. We did this earlier. There's something called scalar multiplication. I don't know. Have I ever said this word before in this class? I don't think so. Scalar. You normally don't have to say this word until you introduce the idea of vectors. Scalars are just numbers. They're one-dimensional vectors if you want, right? Like the number 5 is a scalar. So that's all a scalar is a single-dimensional thing, as opposed to vectors. Okay. So scalar multiplication would be something like if you, good Lord, Jeff, if u vector was -2, 5, then what's 3 times u vector? Well, that's just going to be -6, 15. Okay, that's think up. That's nice. And that makes sense because it would be like 3 of these adding, -2 plus -2 plus -2, 5 plus 5 plus 5, bam. So of course I just multiply through. Okay, good. Now let me show you this really cool website.
See if I can bring back some of you guys with a bit of a multimedia presentation. Mouse, wake up. Oh, where are you, website? There you are. So this is actually, let me make this live up in Canvas. If you go in a minute to unit, where are we at? Unit 10. It's called Interactive Vector Website. Let me show it to you. So if you go to unit 10, you'll see, let me make it look the same as you. Bam. Bam. Okay. Unit 10, you'll see Interactive Vector Website. If you do that, I can't see shit anymore. Hold on. There we go. Can you guys see a website with vectors on it? Yes. Okay. So what's kind of cool about it, I like these little applets that they have here. Here's my vector. So let me pull this in a slightly better place. Okay, over here. So I can move the tail and the head. So what they've done is kind of nice. They put the direction vector and the magnitude lies completely on the x-axis because the magnitude is a scalar, it's a number. So it's just going to be the x-axis. So it's kind of nice. It's not very useful necessarily, but it's a nice visual of breaking a vector down into its direction. And I'm honest, what do you want from me? It's not useful for much, but it is kind of a nice thing to kind of see the breakdown. Okay. Blah, 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 blah. Then the next thing they've got is a nice visual of this. So I can construct, let's make, oh, what was it again? Let's see if I can get that. 1, 3. You can do it, Jeff. Can you do it? Quick and even scroll out. Is that 1, 3? I don't know. No, not quite. Can you do it? I don't want to waste everybody's time. We're going to get close as we can. I don't know. I can't quite get 1, 3. That's all right. That's too bad for everybody. Just do something, Jeff. All right, that's almost 1, 3. Screw it. Okay, that's really close to 1, 3. Okay. And what was the other one? -1, 2, right? -1. All right, why are you not working for me? -1, 2. We can do this. All right. Are you guys doing okay out there? Probably not. You're all like, all right, Jeff, we get the idea. Do you? All right, that's pretty close. Okay, it's pretty close. Oh my God. And then you can see the resultant is basically 0, 5. If you're a little lenient with me, I couldn't quite get it perfect. But you know, you can kind of play around. And again, it's not the most useful thing, but it is a nice visual of what's going on. It kind of snaps onto this. That's neat. All right, there you go. So this is the diagonal of the rectangle. I like it. So this is called the parallelogram method. So you have one vector in standard position, the other vector in standard position. You draw a parallel here, and you draw a parallel here, and then you connect there, and that's your resultant vector. That's how you add two vectors visually. Now, what if I wanted to subtract the two vectors? To subtract, I can actually think of adding the opposite of the other one. So if I want to subtract these two vectors, I can actually just, if I want to do b minus a, I can actually just make a negative of what it was. But what's more interesting visually, let's see if they do this. No, they don't. Those are assholes. All right, let me show you real quick. So if I want to add the two vectors together, I run this way. If I want to subtract the two vectors, I run this way. Let me show you. See there, I go between the two. I don't go from here out. I go between the two, which kind of makes sense. What is subtraction supposed to do? Isn't it supposed to show you how far apart two things are? Wouldn't you say in this picture how far apart A and B? Doesn't X represent kind of how far apart they are? Okay, so on that level, it makes sense. But the nice thing is, to subtract them algebraically, you just subtract the components, right? The X pieces, you subtract them, the Y pieces, you subtract them, done. This is just what it would look like visually. All right. So this is not too bad. The last part to this is one of the freakier ideas. So we talked about scalar multiplication very quickly, right? We would just multiply a number by a vector. That's very easy. Just let that be easy. What the hell, how the shit do you multiply two vectors together? There's not one answer to this. There are multiple answers to this. We're going to talk about one of them. I don't know how deep I'm going to get into it, if I even want to start it tonight. No, I think, all right. We could. So, all right. No, let's not do it. We'll do it tomorrow. I think I've tortured you guys enough for one day. So tomorrow we'll finish out 10.8. We're a little behind, but it's not terrible. We'll get into chapter 11 tomorrow. Some of you guys are like, I'm okay to be behind, Jeff. Slow your ass down. Don't pile more homework on me. All right, I understand. So there you go. I'm letting you out early. Give me a break. All right, so we'll finish up chapter 10 tomorrow. We'll get into chapter 11. Declare chapter 11. Let me know if you need to hang out. Otherwise, you're free. You're free to go. Free to run screaming from the room anytime.
Thank you.
Oh, what was that? What happened?
Have a good one.
All right, you too. That was different. All right, guys, I'm headed out. I'll see y'all later.